Welcome to Dr. Sherry's Astronomy channel. This time, the theme is: the Milky Way galaxy is found to be full of meteorites. The universe is filled with materials that form various celestial bodies, from light elements like hydrogen and helium to heavy elements like iron and sulfur. However, such diverse elements did not exist when the universe was born 13.8 billion years ago in the Big Bang. The newborn universe contained only hydrogen, helium, and a very small amount of lithium. Later, the first stars were born, and heavier elements were synthesized through nuclear fusion inside these stars. These elements were then scattered throughout the universe through spectacular phenomena like supernova explosions that occur at the end of a star's life. As the universe evolved, various spectacular explosive phenomena like supernovas repeatedly occurred, spreading diverse elements throughout the cosmos. These elements transformed into materials that became the building blocks of stars, planets, and even life itself, continuously circulating through the universe. In particular, heavy elements, unlike in the early universe, exist not only as gases but also become solid, forming dust particles that serve as raw materials for planets and meteorites. Among these elements, sulfur, which is essential for life's activities, is thought to make up a considerable proportion when we look at the universe as a whole. On Earth where we live, it's known to be the fifth most abundant element. In volcanic regions like Yellowstone National Park, we can feel its presence up close when we visit hot springs and geothermal features. Sulfur is mainly synthesized by core collapse supernovas that occur when stars more than 8 times heavier than the Sun reach the end of their lives. The frequency of such massive star explosions can be estimated to some extent from the history of star formation in the universe. As a result, we can theoretically estimate how much sulfur has been produced throughout the entire universe. However, long-term research has revealed that the amount of sulfur observed in the interstellar medium, the gas and dust between stars, is significantly less than what these calculations predict. This phenomenon becomes particularly pronounced in molecular clouds, high-density regions where new stars and planets are born. Astronomers have speculated that this missing sulfur might be hiding throughout the cosmos in the form of solid particles too small to see. However, directly capturing this form with previous technology has been extremely difficult. Now, a research team led by Dr. Corrales from the University of Michigan has discovered this hidden sulfur in the cosmos using a groundbreaking method very similar to X-ray imaging used in medical settings. In hospitals on Earth, X-ray photographs are taken to see bones and internal organs inside the body. In X-ray photography, X-rays are shown through the human body, and by examining how this light passes through the body, we can visualize what's inside. In this observation, this principle was applied on a magnificent scale. The research team selected 2 very bright binary star systems on the opposite side of the Milky Way galaxy, about 35,000 light-years away from Earth, as light sources for X-ray diagnosis. One is a binary system called 4U163472, composed of a black hole and a lightweight normal star. This is a representative X-ray nova that periodically shows sudden increases in X-ray emission. The other is GX340+0, a binary system composed of a neutron star and a relatively heavy normal star, known for emitting strong X-rays stably. Both objects were discovered during the dawn of X-ray astronomy, which became a new observational tool in the 1960s, and their properties have been studied in detail over many years. For example, the designation 4U indicates that it was discovered by Uhuru, the world's first X-ray astronomy satellite launched in 1970, and it has been observed numerous times since then. Therefore, these 2 objects are known as reliable X-ray sources and are ideal targets for studying interstellar matter. While we can use such reliable objects as light sources, previous research couldn't make full use of their brightness. This is because, unlike X-ray photographs taken in hospitals, studying the detailed conditions of interstellar matter that X-rays pass through on their way to Earth requires extremely precise measurement of X-ray spectra. Various elements that make up interstellar matter each show absorption at specific wavelengths, in the case of X-rays, at specific energies. To capture these subtle absorption features, previous observation instruments lacked sufficient performance, requiring X-ray spectrometers with high resolution. This is where XRISM, an X-ray astronomy satellite led by Japan and launched in 2023, plays a crucial role. XRISM's greatest feature is that it's equipped with Resolve, a state-of-the-art X-ray spectroscopy instrument. Resolve converts individual X-ray particles coming from the selected targets into heat and detects tiny temperature changes, recording them as signals. This makes it possible to obtain X-ray spectra with unprecedented precision. Sulfur atoms in the interstellar medium are known to create characteristic absorption structures at specific X-ray energies. Resolve can capture this absorption with extreme accuracy, making it possible for the first time to directly determine what form sulfur exists in space, whether as gas or incorporated into dust as solids. When we actually look at the spectrum captured by XRISM, it appears like this. The horizontal axis represents the energy of the X-ray light, and the vertical axis represents brightness, expressed as the number of X-ray photons. 3 panels are shown, but all use the same data. The actual data is shown as a black line, displaying an undulating structure. These undulations represent the state of sulfur, and we need to interpret them. Therefore, the research team used 3 approaches. First, in the upper 2 panels, they assumed that sulfur exists only in gaseous form. You can see that the red models in each don't match the actual data. In the lower panel, they used a model assuming that sulfur exists not only as gas but also as solids, and you can see it matches the observational data. Further detailed analysis revealed that the solid sulfur detected this time is not an unknown substance, but iron sulfide. This discovery shows that some of the cosmic dust consists of materials we know, specifically, the same components as celestial bodies like meteorites. Meteorites widely contain troilite, a type of iron sulfide, which is thought to have played an important role in the formation process of planets like Earth and Mars. In other words, we have obtained important clues for unraveling the grand story of the universe, how planetary systems like our solar system formed. XRISM's discovery has revealed that the previously hidden sulfur exists in solid form, but even when combining sulfur in gaseous form with solid sulfur, the amount observed in interstellar matter is still about 40% short of what theory predicts. So where is the remaining sulfur hiding? Several possibilities are being considered. For example, instead of the iron sulfide detected this time, there might be unknown compounds that haven't been found yet, where sulfur bonds with other elements like carbon or silicon. There's also the possibility that it exists as larger chunks that can't be captured by X-ray observations. While X-ray observations can detect very small sulfur dust particles, if sulfur exists as large chunks, X-rays would hardly be absorbed and couldn't be detected. In fact, recent separate research suggests that this missing sulfur might be hidden in ice, not as gas, nor as dust combined with heavy elements like iron. It's predicted that on ice dust grains, sulfur atoms change into special molecular forms like crown-shaped ring structures called octasulfur, or spaghetti-like chain structures called polysulfanes, and become trapped there. Such insights provide important clues for approaching the mystery of material circulation in the universe. As in today's observation, sulfur exists as iron sulfide dust in molecular clouds where new stars are born. And such sulfur-containing dust becomes the raw material for creating planets, comets, and asteroids. The fact that many meteorites falling to Earth are rich in iron sulfide is evidence that such dust was incorporated when the solar system formed, and some of it remains to this day. Therefore, the widespread existence of similar materials in molecular clouds, not just in our solar system, suggests that countless asteroids, comets, and meteorites have formed and fill the entire Milky Way galaxy. In recent years, interstellar objects like Comet 3I/Atlas from outside our solar system have been discovered, revealing the possibility that celestial bodies rich in sulfur in the form of ice and dust may be far more numerous in the universe than we imagined. Thus, this achievement by the XRISM satellite represents a major step forward in connecting distant cosmic regions with familiar meteorites and comets around us, revealing the connections between materials throughout the universe. Further observations are expected to reveal the whereabouts of the remaining sulfur and the complete picture of material circulation in the universe. We look forward to future developments. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.